was changing the wording a bit. So let me know. We were looking at the set 3a plus b 0, a minus 5b, such that in B are in R. And I think the question is this set of vectors a subspace of R3? So I gave you two parts last time, and I think we finished the one part. The one example, the one subset was not a subspace from last time. In this one now, let's talk about, we kind of mentioned it at the very end quickly, but let's think about whether the answer's yes. Robocall. Yes or no? Do we agree on whether the answer should be yes or no for this? This one's actually yes. And then I think you got to realize it's more than just a yes or no question. You got to justify the why. And the easiest way to justify this is not to go through verifying the three properties, because on my review sheet I gave you of important points, I said one way to show a subset is a subspace is to actually verify the three properties of subspace. But I wouldn't do that here. I would just observe that vectors in this form can be written how? We can write them as A times 3, 0, 1 plus B times 1, 0, negative 5. Now, sometimes you guys like to put, I've seen you guys sometimes put plus a 0, 0, 0 on the end. And if you already have something there, you never have to write plus 0, 0, 0. That doesn't really add anything unless it's all by itself. So if you make that observation that any vector that looks like this, and this is helpful because we can say that this span, or this, nope, I gave it away. That this set can be described in a different way, right? It's all linear combinations of 3, 0, 1, and 1, 0. Of 3, 0, 1, 0, negative 5. And we have a theorem that any span is a subspace. So that can be a What's the difference between, does this all look alike to you guys if I write this? And if I stick the word span in front of it? Because you know who you are. Somebody on your homework didn't write the word span, and I took points off, and they're probably like, how come no fair? So you got to know the difference between these two notations, right? So this is just a set containing exactly two vectors. Sometimes we write a basis in that way, the basis of two vectors maybe. But there are exactly two elements in that set, two vectors. And then the difference with span is this is a set containing how many vectors, right? Yeah, a lot. Infinitely many, probably, right? A set containing infinitely many, in this case, all linear combinations of the listed vectors. So, it's everything you can get by choosing any real number value of A and any real number value of B. So that's why it's a subspace, it's an infinite subset. So just sometimes people are a little bit unclear on the meaning of span, so it's worth reiterating that here. All right, I'm going to erase. We got our pictures. Let's do another one. All right. So that was it. Oh, one more thing I want to say about this, though, just to make sure everybody's thought about it. If I made one little change in this problem, if you had a different constant here, if you had something like 2, then the answer becomes no. You could describe these with a 2 as plus, just like our general solution to a system, we might describe in this way, 0 to 0. But when you have to write a constant vector on the end, say a non-zero constant vector, this description no longer works. You can't describe it as a span of vectors. It's a span of vectors with everyone getting this constant vector added on the end. So it's not a subspace anymore. And why? We mentioned it last time, but I just want to make sure everybody knows. There's an easy answer why. You can't just say it's not a span, because a subspace doesn't, well, every subspace is a span of something, but just because it's not the span of those two doesn't mean it's not a subspace. You could try to verify the 3 properties, and right away you'd find out what's the short answer here for y? 0, 0, 0, 0 is not in this set. There's no way to get 0, 0, 0. No matter what you set A and B equal to, if you set them both equal to 0, you're always going to have 2 in that middle entry. It's easier to see back here that there's no way to get 0, 0, 0. It's actually easier without this expanded form. Okay, so So when a subset is not a subspace, if we're lucky, it's not a guarantee, but you might just be able to observe that the 0 vector is not in it. If not, you really do got to go through those properties. Sometimes you've had homework problems, right, where you showed a subset was not a subspace in other ways, right? Wasn't there a couple homework problems where sometimes one of the other properties was not true, where the sum of 2 vectors in the set was not in the set, or a scalar multiple of 1 was not in the set. So we should just say there are other ways to show a set is not a subspace. So I don't want to leave those out. Okay, let's do something else here. Let A be the following matrix: a column 1, 0, 2, 1, 2, 0, 4, 2, 1, 3, negative 1, 0. Find a basis for each of the following: null A, column A, row A. So these are three subspaces of our n's. And this is pretty much a crank it out kind of calculation. I'm going to let you work on that for a while on your own and give you a couple other. There's a second one, and I think I'll put one more on the board before we start doing these together. Everybody, we're all sniffling today. These were each taken off of last semester's exam. Yeah, Jim? About rank? Yeah, oh yeah. Worry about rank. Well, let's do these and then we'll talk about rank a little bit maybe. so before we do those, I'm just going to make John worry a little bit. The way to get a handle on rank is to just think about the number of columns of a matrix. And let's try to think in generality. So A is an m by n matrix, so n columns. Just focus on the columns for a moment. When you reduce that matrix, the columns are either going to be pivot columns or not pivot columns, right? Some will have pivots, some won't. And the number of pivot columns plus the number of non-pivot columns is the total number of columns, and that's n. If it's m by n. This is where that equation involving rank comes from. And this is how I remember it. The number of pivot columns is the same as the dimension of the column space of A. Right? When we reduce, we find out where the pivot columns are. In fact, you're going to do that in that other problem. Then you go back to the original matrix to pull out the basis vectors for the column space. The number of non-pivot columns, I would say these correspond to free variables in the solution to AX equals 0, the homogeneous equation. And the number of free variables in the solution to the homogeneous equation tells us the dimension of the null space. I think you got to just memorize, even though it's not hard to think about why it's true. The dimension of the column space equals the dimension of the row space of A. And that's equal to the rank of A. So if you're just told the rank, these are all the same thing. 3 different ways of saying the same thing. And I put column space first because it's easier to see where this equation comes from the column perspective. But of course, the final form of that theorem, it's usually written as rank A plus the dimension of null A equals n. So I memorize it in this form. And I just remember that dimension of column A is the same as the rank. And we'll do something with that in a bit, but yeah, you got to know how to answer questions using this. Okay, now I wrote all over the place. So for this first problem we put on the board, the most work involved, I think, is in finding a basis for null A. So we got to try to solve AX equals 0. And so you're going to reduce system. Even though you don't have to write the zeros on the end, you could just reduce A. Because when you're solving the homogeneous equation, that B column of the augmented matrix is just zeros all the way through. So that's why people don't always write it down. I'm just going to write down the reduced form. Now, I try to make this not complicated. I can't guarantee there will never be fractions. Sometimes fractions will appear because sometimes people go through the steps in different ways. So please don't panic if you get fractions, but it should not totally get out of control. I'm not going to give you something that just becomes a nightmare. So if it's getting really, really bad, you might wonder if you didn't make a little mistake along the way. So this is the augmented matrix reduced. And we can see a pivot position here and here. There are just three variables, x1, x2, that 0 augmented column on the right. So x2 is the only free variable, I would see, right? And as soon as I see that I only have one free variable, I know the dimension so the dimension of null A has to be 1 here. To get a basis, I think I have to write out the general solution. So I have x1 plus 2x2 equals 0 from the first equation. Then I have x3 equals 0. So my general solution is going to look like negative 2x2. x2 is free. x3 is 0. So you guys should be pretty comfortable with this process. Now, we solved the system, but we still got to answer the question. We got to find a basis for the null space. So basis for null A is a set consisting of just that one vector. It's a one-dimensional subspace in this case. There's no guarantee, it's not necessarily one-dimensional. Could be two-dimensional, could be three-dimensional in this example. You could have a three-dimensional null space. So sorry, I'm kind of squeezing it into my leftover space here. Now, once you go through that work, the basis for column A and row A is all set up for you already. So you don't start all over again. Yeah. You're just going to fill in the answer for column A and null A. Basis for column A is, what's the dimension of the column space? 2, right? I mean, now, if you're looking at this rank equation, you might say, wait a minute, weren't there 2 non-pivot columns? Is that bothering anybody here when you look at this? So the rank equation applies only to the original matrix being reduced, not the augmented matrix. So it only talks about A. So in that rank equation, there's only one non-pivot column, 2 pivot columns. The n for A here is 3, all right? So I just like to write the zeros on the end because that's what we always did when we were solving AX equals B. And so I know the dimension of the null space plus the dimension of the column space has to add up to 3. So as soon as I know the basis for the null space has 1 vector, basis for the column space has to have 2 vectors. And there's one thing you got to be careful about. Please don't make this mistake. Some people made it on the homework. To get the basis for the column space, you got to do what? You got to go back to the original matrix because the dimension stays the same, but when you row reduce, you actually get a different subspace from the 2 pivot columns. it's, again, same dimension, and also the linear relationships, dependence relationships are the same in the original matrix. So I know the first and the third column have to be linearly independent. So I can take 1, 0, 2, 1. They correspond to the pivot columns, right? And 1, 3, negative 1, 0. I cannot take, if you take sometimes you can pick any two, but I cannot take the first and second column here as a basis for the column space. Do you see why? That definitely will not work if I take the first and the second, because the second column is a multiple of the first column. So the dimension of the space spanned by the first two columns is just dimension 1. It's a basis of the space. That's the span of these two columns is just 1. However, if we're not saying the only basis is the basis that you get from the columns corresponding to the pivots, because you could take the second and third. They would work perfectly well as a basis for the column space. But let's not. This is easy. Determine if W is in null A. I guess I'm not going to even carry out the calculation. Null A is, W's in null A. What do we check?
See if it gets mapped onto the 0 vector.
Yeah, so, and to me this is easy, just multiply, right? Take A times W and see what you get. If it's the 0 vector, W is in the null space. If it's not the 0 vector, W is not in the null space. And how do you determine if W is in the column space of A? Yeah, you actually have to solve AX equals W, which may take a little bit of work, right? Consistent or not consistent? Now, there could be shortcuts. Is that where you guys are?
Oh, we were just saying that we had to do it a few times because we got ugly numbers. Are there fractions?
Did I get ugly numbers?
Not ugly, but you know.
No.
Oh, so I probably just messed something up. It's probably just do that.
Unless I copied it wrong. Maybe I
Oh,
copied the
no.
wrong.
I trust you over my.
Oh, I did. No. I did. Sorry. Double. My test problem had a 2 here. All right. So it does. Sorry about giving you something ugly. And, all right. So, of course, now I can't give you an answer to what I wrote originally because that wasn't my test problem. My test problem had a 2 here, so I gave you another practice problem. So for my corrected problem, okay, this is, I think, yes for this one with the corrected problem, okay? And this is no, so I think it's just good practice to again, don't do the one I gave you originally, do this one, and because I don't have an answer for the one I gave you originally, and just verify that the system is inconsistent. That's something we haven't done in a little bit of time, right? What if you just checked to see whether the A was invertible or not? If A is invertible, can you answer these questions? Like,
If it's invertible, that means null A is 0.
yeah, if it's invertible, null A only includes the 0 vector. So if it's invertible, this W is definitely not null A. If it's invertible, is W in column A? Yes, it must be, because the 3 by 3 matrix represents a transformation that's onto, both one-to-one and onto, right? They go together with square matrices or transformations from Rn to Rn. If it's not invertible, what do you know? Can you draw any conclusions just from the fact that it's not invertible? I don't think so, right? So I don't think it's that great to go down the road of trying to see if this matrix is invertible, because if it's not, you haven't really shown anything. Same thing with determinant. If the determinant is non-zero, great, you can answer that question. But if the determinant is 0, you can't answer the question based on that. Okay, this guy, let's erase some. So make sure we can go through this calculation. So, and I'm also, I just want to, we'll come back to that row thing. So I have, but trying to think about that in the back of my mind as we go through these other ones. So I'll have something to say about the row space answer. So steady state matrix, or steady state vector. I think you just sort of have to know what the process is, right? We want to solve AV equals V, or AV minus V equals 0. And to factor out the vector V, you need an identity matrix times the vector written in here. And so we can write this as V equals 0. So actually, this is what we end up solving. The A minus I vector is, what, 0.4, 0.6. I have 0.1, 0.9, minus 1001. And 0.4 minus 1 is going to be negative 0.6. 0.1, 0.6, 0.9 minus 1 is negative 0.1. Yes, you always kind of get something that looks like this. And so if we want to solve this system, our augmented matrix for solving the system is going to look like negative 0.6, 0.6, 0.1, negative 0.100. Just homogeneous system. And as we row reduce, here we're going to get pretty quickly to that last row being all zeros, right? We can just add the rows together. And if I divide by negative 0.6, I just want to say, I'm not going to go through all these steps. And what I'm going to get is the general solution looks like this. If V is, say, a V1, V2, it can be described as V2 times 1, 6, 1. Well, I guess I almost filled in every step. And you're not done yet. So just this one thing you want to make sure you know when you go through this problem, that we're not just solving that equation. What's the one additional thing we need to do? We need what's called a probability vector. Where the entries add up to 1. So while there are infinitely many solutions to that system, we need the particular V where, think of these as 1/6 V2, V2 is another way to describe that general solution. We need 1/6 V2 plus V2 to equal 1, and you got to solve for V2. So you actually solve for a particular value of the scalar that gives us one very particular vector. And here V2 is 6/7. So our probability vector V that we want here turns out to be 1/7, 6/7 in this case. That would be the answer. All right, so let's just go back, talk a little bit about row space. And so you guys are absolutely right. So if you're interchanging rows and you want to go back to the original matrix, you have to go back to the, you kind of have to interchange back to where those rows were originally. And let's just look at a simple example of that. So row space basis. If A is 0, 0, 0, 1, 0, 0, 0, 1, 0, and you row reduce, you're basically just going to interchange some rows to row reduces, right? We want the 1, 0, 0 in the first position, 0, 1, 0, 0, 0, 0. And so a basis for the row space of A is going to be 1, 0, 0, and 0, 1, 0. So you can, here are our two pivot positions. We can take those two rows. And you absolutely cannot take the first two rows of the original matrix, right? This is the point you guys were all trying to hit me over the head with. And so you would have to follow those back through the row operations to go back through the interchanges to where those rows originally came from. The only rows from the original matrix that you can pick as basis vectors for the row space are this one and this one. And they correspond to those two, but things got moved around. You just can't line up and say, I'm going to take the first row. And this example should hit you over the head. All right. However, with the column space, you really can just go back to the original matrix and take the columns that were in those positions. So sorry, I was very unclear about that a moment ago. Does this help a little bit, or just now? What am I?
The comments in the row vectors, is that that's typically
I don't think you have to, but it gets really hard to look at handwriting.
easier to read it? Okay.
So I can't remember our book's convention exactly on this. I think they tend to just use parentheses for the row vectors. They just go back to good old-fashioned ordered triples or ordered pairs or whatever. So I'm not gonna zing you on that. Just again, we've done so little with rows. What did I write on my solution when I did it? Yeah, I actually, in my answers, I didn't write commas, but I wrote them horizontally, so I don't. That's just a convention to make it easier to look at. It's not a law about how that's got to be written. Okay, there's one more thing. All right, so I want to do something a little bit more abstract before we, unless somebody's got something they really, really, really want to bring up. So here's an exercise. Something a little bit more theoretical, a little bit more abstract. A is an m by n matrix. A is equivalent to U in row echelon form. So U is a row reduced. Suppose U has K non-zero rows. What is the dimension of the solution space? Oh, I got it. Of AX equals 0. A is m by n. A is equivalent to U in row echelon form, so use the row reduced version. U is the row reduced version of A. Suppose U has K non-zero rows. What's the dimension of the solution space of X equals 0? Well, it's probably going to have an M, an N, or a K in it somewhere, right? It's not going to be an answer like 2 or 5. dimension of the solution space of AX equals 0, what do we call that? Yeah, that's a dimension of the null space. What is K?
It's a dimension. Row
Yeah, K is the number of non-zero rows. So when you're in a row echelon form, not necessarily reduced all the way, so I added these words. So not necessarily all the way, just in echelon form. Maybe we should just take this. But once you get to echelon form, you know where your 0 rows are. And any row that's not a 0 row has to have a pivot position in it. So there are K pivots, K rows with pivots. What's that the dimension of? Yeah, maybe it's a little easier to say first. That's the dimension of the row space of A. So you're going to get a basis vector for each non-zero row in that echelon form. But the dimension of row A is equal to the dimension of column space of A is equal to the rank of A. So this is the problem for Jen, right? So this is where I think you got to fall back on this idea that the rank plus the dimension of the null space of A always adds up to something. And so make sure you got the right one. Yeah, N, not M. So it's always number of columns, just in case you have actual numbers there. And so what are we saying? We're saying this is K, right? We're trying to figure out what that is. We know the number of columns is N, so that what's the dimension of null A has to be? Well, I think we can say exactly, yeah. I mean, we're saying this is exactly K. So I think we can say N minus K, right? It's just like solving for question mark. Question mark has to equal N minus K. So there's an example where relationship, right? Okie doke.